Hello everyone, and thank you for attending today's webinar, How to Evolve xHaul Networks for 5G, sponsored by Anritsu, Ericsson, Fujitsu, and Infinera. Before we begin, I want to cover a few housekeeping items. On the left side of your screen is the Q&A. If you have any questions during the webcast, you can type your question into the Q&A box and submit them to our speakers. All questions will be saved, so if we don't get to answer you, we may follow up via email. At the bottom of your audience console are multiple application widgets you can use. If you have any technical difficulties, please click on the yellow Help widget. Here you can find answers to common questions. A copy of today's slide deck is available for download in the green Resource List widget, as well as some other assets made available from some sponsors. Towards the end of today's presentation, we'll ask for your feedback. A survey will pop open on your screen, and will only take 1 minute to complete. Your feedback is extremely helpful. An on-demand version of the webcast will be available about 1 day after the event and can be accessed using the same audience link that was sent to you earlier today. I would now like to turn the event over to Heavy Reading's Principal Analyst, Sterling Perrin. Sterling?
Thank you, Reagan, and hello, welcome everybody to today's webinar. We do have an interesting project we're highlighting today, so an interesting webinar, lots of good data, and hopefully everyone enjoys it. The webinar it's actually a readout of part of a larger multi-sponsored project that the sponsors, of course, being Anritsu, Ericsson, Fujitsu, and Infinera. And the basis of this project was a global survey we did of Heavy Reading conducted of 86 operators on the topic of 5G transport. And it's actually the second year running on this project, so we're actually amassing quite a bit of good data at this point. The survey part for 2020 is complete, and we'll share some of the results. I'll share some in a bit, and then as we go through the course of the webinar, sharing some of the findings and discussing the trends. The white paper portion is being written now, and we expect that to be available to attendees here by the end of the month. And so joining and kind of helping me walk through the data and talking about some of the larger trends, we've got 4 speakers on behalf of each of the sponsors. You can see them here. I'll let each of the sponsors just give a brief introduction of themselves and their companies where they think it's valuable, just so you know the perspectives that we'll be going through today. And with that, let me just move it right to Tim from Infinera to give an introduction.
Hello, everybody, and happy to be with you here today, and thanks for joining. Thanks, Sterling, also for the introduction and the good work on the primary research that just got completed. So at Infinera, we believe that 5G requires a mobile transport toolbox. Given the networking changes that are happening with things like diverse frequency bands and RAN functional splits and advanced service delivery, a one-size-fits-all approach to the transport network won't work. We're thus working very hard to either enhance or deliver a collection of capabilities, including auto-tunable DWDM pluggable optics, Ethernet-based front-haul solutions with time-sensitive networking, point-to-multipoint XR optics with individually assignable Nyquist subcarriers, enhancements to packet optical transport, and also disaggregated routing with our ongoing collaboration with the Telecom Infra project. Finally, all of that is being done with intelligent software automation that is needed in order to provide actionable intelligence and also to simplify the overall operations. Thanks again, everybody, and happy to be here.
All right, excellent. Thanks, Tim. And moving along, Daniel Gonzalez representing Anritsu. Daniel?
Yes, thank you, Sterling. For those of you that aren't familiar with Anritsu, we are a global provider of microwave RF and optical test and measurement transport equipment. Some of our most notable test and measurement products include the field portable RF spectrum analyzers and the optical transport network test equipment. So for this presentation, we're really bringing a perspective from what's being done as far as measurements and challenges that we've discovered in the field when deploying 5G transport networks. Thank you, Sterling.
All right, excellent, thank you. And moving to Joe Masserino, who's representing Fujitsu today.
Thank you, Sterling. With expertise and proven track record on 4G and 5G transport using our smart xHaul system, Fujitsu offers smart power and some of the largest network service providers in the world. We are a market leader in 5G TSN-based front-haul and Pico small cell transport solutions. We lower the cost with pay-as-you-grow and ultra-scalable architecture using SCN control, automation, and AI. Our cloud-based routing solution provides new routing economics for a 50% TCO reduction. Fujitsu is open, critical in building a carrier RAN neutral transport proven to interwork in a multi-vendor environment with different xHaul architectures. And finally, our services team uses Fujitsu and our partners' hardware and software to build custom yet open transport and vRAN solutions. Thank you.
All right, excellent. And last but not least, let's bring in Kevin Murphy. Kevin representing Ericsson. Kevin?
Hey, Sterling. Thanks very much for inviting us. My name is Kevin Murphy. I work in the 5G transport team, little blue box there on the left in Dallas. As you know, we're one of the biggest radio system providers globally. We have 100,000 employees and about 10,000 here in the U.S. We're really focused on 5G now all across the whole company. 5G has just exploded compared to the other Gs. I've been around for all the way back to 1G, but we have 40 live networks in service today and about 75 contracts. So it's a huge impact on transport. What we're going to see and what we'll be speaking about in the coming slides are the diversity of different services that are emerging now. The growth is going to be in Internet of Things and machine-type communications, enhanced mobile broadband and fixed wireless access. So there'll be new revenue streams and new types of transport infrastructure. On the right, you probably can't see the details there, but we have a very broad portfolio of products, including antenna systems, dozens of different kinds of radios, and then RAN compute, which used to be the baseband subsystem. It's now evolving to a cloud-based RAN control system. And then my area, which is mobile transport, it's optical transport, microwave transport, and routers, basically customized for the RAN environment. And then lastly, site solutions. We obviously have to make the infrastructure as deployable, as easy to roll out, and as inexpensive as possible. So we optimize all of the, I guess, hardware and components in a cell site. So that was it. Thank you.
All right. Yeah, thank you. Thanks, everybody. So, and also for the audience, that should give you a different sense of the different voices that you'll be hearing from throughout. The format is I'll introduce things pretty briefly with some of the high-level data from the survey, and then we're really going to have a discussion-based format across the rest of the topics you see here. So we have different companies, different perspectives. We want to bring those in. And hope to have about 10 minutes for your questions at the end. So please do ask those as they come to you throughout. In terms of the survey itself, here's a quick look at the demographics. The pie chart is the geographic breakdown. As I said, 86 respondents, 57% North America, and rest of world combined for everything else. We conducted the survey in May of 2020, and every respondent was involved in network planning and or purchasing, and also a good representation from large companies of over $5 billion annually. That was 55% of the survey group there. We wanted to get, right from the start, you want to get a sense of where are operators in terms of moving to 5G generally, and based on the survey results, you can see initial launches are already underway for many, I think consistent with what the sponsors here will tell you in their own interactions. 38% reported they've either launched initially or plan to by end of 2020. So we broke this out by initial launch as well as mass market launch, which is the reddish shade in these bars. So mass market, you can see, hasn't happened yet, but it's actually not that far off. If you add up 2021, 22, and 23, you get to 63% of the survey group expecting mass market launches in that time frame. We do see variations by operator size. I don't show it here, but just to give you a flavor, North America tended to be more aggressive than other regions in terms of their launch dates, and also by company size, larger tier ones tend to be more aggressive, and also by region, North America tended to be more aggressive versus other regions. Although we didn't ask about COVID specifically, you can see this was done in May, so you can assume some of the thinking around COVID was already kind of baked into these results, as you know, a lot of the implications of that were already known by then. This is actually late May that we did the survey. The last bit I'll show up front is transport network upgrades. Of course, we want to understand, this is a transport project, we wanted to understand where operators are in upgrading their transport networks to support 5G. And we broke this up by the different xHaul transport segments. Front haul is the blue, the red is mid-haul, and the green is backhaul. And the findings here, backhaul and front haul are definitely furthest along in terms of the percentage reporting. Either they've already begun upgrades or expect to have upgrades done by 2020, by the end of the year. Backhaul and front haul kind of leading there. Mid-haul a little bit lagging behind. You can see the reddish is lower in that first category on the left, but actually accelerates throughout, and they're pretty evened out. You know, if you add them all up by the end of 2023, front haul, mid haul, back haul, you know, largely either underway or certainly completed by then. Interesting, or you know, maybe as expected, few see no need for transport upgrades in that time frame. And again, looking at regional breakouts here, or you know, breaking out by company size, we do see tier ones being more aggressive in upgrading, particularly on the backhaul side. Actually, they stood out, which is pretty consistent with what we've seen with migrations from 1 gig to 10 gig in backhaul networks. I think that's reflected in these results. So with that, let's move right into the discussion portion, if we can. And I'll bring in Kevin to kick that off. How does the choice of radio in 5G affect the transport network? I'll let you start us off on that one, Kevin.
Okay, thanks, Sterling. Yes, good question. But probably more accurately, I would say, how does the 5G radio access technology affect transport? Because, as you know, 4G and 5G are a little bit different in the way that it works over the air interface. We have the ability now to use much wider bands in the spectrum, and also to move up to higher parts of the spectrum. So, for example, millimeter wave. You couldn't use LTE over millimeter wave. Now you can, in fact, use extremely wide bands, maybe 400 megahertz or even 2 times 400, which is 20 times more than you could in an LTE band. So I'm going to look at 3 different types of 5G radio that's being introduced and how they affect transport. Typically, we started off with millimeter wave. We're going to rapidly move towards C-band with massive MIMO. And then we have this thing called dynamic spectrum sharing, which I can speak about a little bit as well. So millimeter wave, by its nature, doesn't have very long reach. It tends to be used on utility poles or you know, close to the end user. However, it can have a huge amount of bandwidth. So the connectivity to that particular radio is typically in the order of maybe 2 times 25 gig if you're going to do a front haul interface. But you can, in fact, do a backhaul interface to a millimeter wave radio. Also, we've got little small outdoor basebands that are combined with the radio. So that's one thing. We've now got this challenge to how do we connect this amount of bandwidth to a small utility pole. You can, of course, use wave division multiplexing, and there's the question of placing these millimeter waves on pre-existing poles that already have 4G radios. So you'll end up with, perhaps a number of different front-haul facilities. Saving fibers or utilizing fibers effectively is key. So there's a number of transport technologies that will be needed to utilize that as effectively as possible. When we get to massive MIMO, the concept of massive MIMO, you can have a 64T, 64R radio, which is basically, it's like a matrix of antenna elements. Now, that'll be 4,096 antenna elements, so if you've got data coming off of each of those, you obviously wouldn't be able to connect it to a baseband. So this concept of the lower layer split takes some functionality from the baseband, moves it into the radio in order to process the massive MIMO antenna signals into something more manageable, which we call eCPRI, or it's an Ethernet-based front-haul protocol. So massive MIMO is driving this need for eCPRI type of protocol, because raw CPRI coming out of a massive MIMO antenna would be way too much data. So along with that, then we have a change in timing and synchronization, because CPRI fronthaul, the original fronthaul protocol, had embedded sync. It was a synchronous flow of bits, so you could have a synchronization plane built in. Now with the packet-based fronthaul, we need to start using 1588 precision timing protocol. And not only that, we're introducing TDD radios, time division duplex, which have a much tighter constraint on synchronization, because you have upstream and downstream transmissions being timed, and if they're out of alignment, they will, of course, interfere with each other. And then we need to think about how 5G gets overlaid onto 4G. Obviously, we can't just forklift out the 4G and replace it with 5G. So it has to be a phased approach where 5G is overlaid and combined with 4G. So the current infrastructure of baseband units can, in fact, simultaneously serve 4G and 5G. We have this concept of mixed mode basebands, where some of the radios could be 4G, some could be 5G, and then another concept called dynamic spectrum sharing, where a radio can actually have on its air interface both 4G and 5G protocols. So that brings up the question of there was one of the questions was regarding the split, the disaggregation of the baseband. Well, if it's the same baseband carrying 4G and 5G, that impacts your decision on how you do that kind of a split. And then the biggest question, which we will speak about in some detail, is to centralize or not to centralize. I think the way it will evolve is that there will be distributed DRAN type in perhaps rural or less dense areas, but in the dense urban areas, I think we're going to see more centralizations for economics and OpEx type of reasons.
All right, so let's a lot in there, a lot to unpack. Let's and of course, but it does a good job of setting up basically the rest of the discussion. So let's get into, the transport implications of everything that Kevin just stated is essentially what we're going to focus on. So let's continue with that, and let me bring in Tim to start that off, and then I know Joe from Fujitsu also has some comments to make here. But Tim, I'll let you take this one to start. Transport network implications of centralizing the RAN, moving to these CRAN architectures.
Thanks, Sterling. I thought I would bring a little graphic in. Partly covers some of what Kevin just covered, plus lays out the path here. So, we started life in 4G with I'll just call it a combined radio and a set of electronics in an eNode B, and some of the market evolved to separate the electronics, if you want to call it that, or the baseband unit, from the remote radio head in the 4G network. Now, all of the market obviously didn't do this. Some North America, some APAC, little Europe went down this path. But one of the things we found with this was, because the remote radio head is so, I'll just use the word unintelligent or less capable, we end up with this CPRI fronthaul traffic being very high capacity. And so if we have 1 gig that we want to go over the air, we can end up with 16 or 30 gig needed from a front haul transport perspective, just to kind of put a size on that. And so when we get to then 5G, we actually went back and kind of re-looked at this electronics piece of it and the baseband unit, and we're actually redistributing the baseband unit into really portions of it into really three functions or three areas. One is we're putting some additional intelligence back into the radio unit, so that at this low-fi level, so that we can be more efficient in our transport, and part of that is tied to this eCPRI communication between the radio unit and the distributed unit. And then we're also further subdividing the baseband unit into this distributed unit and centralized unit. Obvious ramifications from that are that now we have to support a front haul, a mid haul, and a back haul type of functionality in the transport infrastructure. And we have to support those collection of entities, RU, DU, and CU, in all kinds of different cases. They could be combined into a GNB, or they could be separated and disaggregated and distributed in different locations. So that puts the onus on the transport infrastructure. And then when you say, what does it mean for transport? Well, we still need low latency and better latency than we had before. We're increasing the capacity. We're needing tight timing and synchronization, especially as we add, Kevin mentioned TDD, great comment, because you need now frequency and phase, and that makes it a little harder. We also need flexibility for the future in terms of services beyond enhanced mobile broadband to get to ultra reliable low latency, and of course always cost optimization with fiber efficiency and automation plays a role here. And with that, I'll pause and let somebody else here chime in. Maybe Joe.
Joe, I know you wanted to make some comments, and we do have a bit of survey data. I'll just push that out so folks can see it. But Joe, thoughts on Tim's discussion as well as on the survey data we have here?
Sure. Thanks, Sterling and Tim for setting that up quite well. The mobile network operators will need fiber facilities to make all of this happen. This means that either they'll utilize existing fiber facilities or have a mix of leased dark fiber along with lit services. And unless they have an abundance of fiber to every macro site, whereas some service providers have that, others do not, they're going to need a fiber relief solution, and preferably a managed to maximize their service availability and minimize OpEx. For a front haul fiber relief, there's, as was mentioned by both Kevin and also Tim, there's WDM, but then there's also the newer TSN based, and to a lesser extent, microwave and millimeter wave solutions that can also provide a level of fiber relief for the transport capability. And TSN front haul platforms, they're fairly new, but they provide a significant TCO advantage, or total cost of ownership advantage, over active WDM. Active WDM or passive WDM was used traditionally for 4G transport, but with TSN, it's about half the cost, about 75% lower, smaller footprint, and about a 90% turn-up time improvement using automation. So just some of the points that I just wanted to mention about centralizing the RAN.
Okay. Anyone have any final thoughts on this one or comments on the survey data itself, which, actually among the architectural options, it was pretty evenly split. I guess with the caveat, I would say that one of those buckets is a traditional distributed RAN, and the other three, so other 3/4 roughly, are some iteration of a centralized to partially centralized. So there clearly is a momentum around moving to some level of centralized RAN.
I think one thing that you might not see here, the question is about 5G RAN functional split, and obviously the functional split are there for a reason, that they're necessary, for the lower layer split simply because of massive MIMO antennas, and we get efficiencies by putting the upper layers into a cloud or a virtual machine. But you need to think of the 4G infrastructure that's out there already. There are tens of thousands of basebands there too. So do you do the same split with the 4G as you do with the 5G? So you've got a choice. Do you centralize your 5G and not centralize your 4G, or and if you have both 4G and 5G on the same site, it makes it a little bit more challenging to figure out how you do this kind of split. But there's some of the topics we'll discuss a little bit later.
Yep. Yeah. No. Good points. Actually, while you're
could I just add?
Go ahead, Tim.
Sorry.
Sure.
I was just going to add one other thing, which is, and it differs even inside the same service provider, 4G, 5G, yes, but then the frequency bands too, because as an example, depending on how much bandwidth you have in millimeter wave and the fact that it just doesn't reach that far from a distance and a propagation perspective, and you may have a decision there that you're going to have RU and DU combined into a single deployment, package, in part because you're not necessarily looking for carrier aggregation, kind of multi-radio performance in that kind of single package entity, versus what you might want to be doing about more of a radio cluster approach with the midband and the low band. Just a pause.
All right.
Yeah, I think you will do different functional splits for different kinds of use cases. So to your point, millimeter wave is particularly onerous when it comes to front haul. So you could consider moving the baseband out. Then you might have a different scenario if you're talking about a rural, LTE site. Maybe you might not need to centralize at all.
Hey, Kevin, since you're on right now, let me just advance it to the next topic, which is about packetizing the front haul network. Clearly, a lot of focus around the architectures falls on, at least the discussion, falls on the front haul. It's new. There's a lot of challenges there. Joe, in his comments, mentioned TSN for front haul as one of the packetizing options. So I'm sure Ericsson has some thoughts there if you want to kind of give an overview of this one, and if anyone else wants to comment,
sure,
we'll bring them in.
Yeah, and it's not just how, it's the why, and it's quite a big debate going on right now. But if you move, I can move to the next slide. I think here I got a little picture kind of illustrating it. So basically, there's a number of different types of interfaces we're going to have to manage here going forward. We have in 5G, we have the high band, mid band, and low band, and of course we've already got the 4G radios in the lower band. So we're looking at how do we transport? Well, first of all, the eCPRI, or the packetization of front haul, initially arose because of this problem of having so much data coming off a massive MIMO antenna, and by virtue of it going into Ethernet frames, of course, it helps. It makes it easier to transport, because now it becomes more like other transport infrastructure. So I think one of the objectives here is to build a unified layer 2 infrastructure that can support RAN, enterprise, and residential, especially for the bigger operators who have a wireline affiliate as well as the RAN. But by unifying this infrastructure, it becomes a lot more efficient. But then we have this problem. So the blue boxes here are basically CPRI to eCPRI converters, or CPRI to ROE tunnels. So there are different ways we can take this legacy interface and bring it over a layer 2 infrastructure. So basically, a packet front haul or a front haul gateway device is like taking a part of the baseband and moving it out closer to the antenna. So the legacy CPRI interfaces can actually be converted to an eCPRI packet based, and then of course you can merge it with other types of services. So on the left hand side here, we've got potentially Ethernet services. Some basebands could remain on the macro site, and you'd have backhaul services coming from those. You could have legacy 4G, CPRI 3, 5, and 7. They're the lower CPRI rates of the older radios. And then the mid and low band, C-band radios. Some of them could be eCPRI, and some of them might be CPRI. And then, of course, we mentioned millimeter wave. Because of its low reach, it tends to more often be on, the likes of a light pole, and it will be coexisting with 4G radio. So you might have maybe 2 25 gig interfaces to the millimeter wave, and then perhaps another 3 CPRI interfaces to the 4G radios. So there, I think there's still a play for wave division multiplexing to collapse all of those flows down onto one single fiber. However, you could also, at the hub site, by converting these flows into a packet format, that gives you this kind of cross-connect flexibility where any flow coming in from any radio can be cross-connected to any baseband. And that really helps a lot with evolution, because as you add and move and upgrade basebands, you need this facility to be able to cross-connect without having to just jumper fibers all the time. Another thing to keep in mind on the bottom here with the evolutions of the function splits, we've had up until now the sort of CPRI consortium split, and everybody has chosen a different name for the radio and the baseband. But eCPRI today, the CPRI consortium variant, the radio is called the ERE, the radio equipment, and the EREC. 3GPP, as we mentioned, has got this RU, DU, and CU. But moving forward, we also have virtualized versions of the digital unit and the distributed and central unit. And then we have this ORAN split. All of them are similar, for similar reasons, but slightly different from different perspectives. So we have to build a platform that can evolve through all of these. It's doing CPRI today, it might be doing virtualization tomorrow, and then ultimately maybe we'll be doing ORAN type protocols in the future.
Great.
So any questions on that?
Good. Yeah, no, good points. Good explanation on the different terminology as well. I find that very helpful. Anyone on the panelists general agreement with what's been outlined? Any other points to make before we move? We're going to talk about testing in a minute, but before we move there.
Sure, I would just like to add a point to that, Sterling.
Sure.
So Kevin had laid that out very well. I would also like to say that, there's a number of terminologies or new terminology that's been discussed here. And, the good news is that there are standards for all of this. So it's well known. This provides for connectivity, smooth connectivity, at least on the transport, for multiple use case applications. So things like we talked about TSN, there's an IEEE 802.1 CM standard, which is specifically TSN for front haul, that's used in these applications. Taking CPRI, which is not packetized, and packetizing it using another IEEE standard, 1914.3, which is the radio over Ethernet capability. This provides an Ethernet encapsulation of CPRI. And then also the legacy transformation into working that Kevin had mentioned. There's multiple methods of doing this. There's the CPRI co-ops version, the eCPRI 2.0 interworking, and then there's an ORAN Alliance version, the low-fi processing capability. But both offer that CPRI to eCPRI translation, essentially an integration of your 4G into the 5G network to provide a level of consolidation.
Okay.
Just one other quick point, Sterling. What this infrastructure shows is what a couple of the big tier 1 operators are doing, and that is transport over a point-to-point fiber, dark fiber network. When you begin to, as Joe pointed out, when you begin to mix time-sensitive flows with non-time-sensitive flows, then you do need this time-sensitive networking with frame preemption to make sure the time-sensitive flow doesn't get delayed or jittered in some way. However, if you build a point-to-point fiber and you run, let's say, a 100 gig interface, which is what we're showing here, you've got the buffers spool out so quickly into a 100 gig pipe that frame preemption doesn't buy you an awful lot. It's definitely a very valuable protocol. and is needed in some scenarios. But the larger your bandwidth on your pipe and the fewer hops that are involved, you don't get much of an advantage, especially the frame preemption in particular.
All right. Yeah. Go ahead.
Go ahead, Sterling. Go.
Oh, I was just going to say. So if you have final words on this, go ahead.
Okay. No, I was just going to say the good comments all around, Joe, Kevin. The only thing that I've kind of personally been hesitant on is the CIPRI to eCIPRI interworking as like a gateway function, right, or an interworking function. Just caution around wanting to make sure latency goals are achieved and we retain an open, interoperability and an open functionality as we look at these logical functions and splits is just something we ought to keep in mind as we look at that function, which is certainly applicable, and I understand those who have deployed a front haul solution already. But there are certainly lots of customers who have not done that yet either. And so that's just something to pay attention to. Yeah.
No, good points. And we're going to circle back to open in a minute. So maybe we can kind of delve a little bit deeper on that shortly. Before we do that, though, I do want to, Danny from Enritsu has been patiently sitting through the discussion and a bit of the debate, but I do want to address the testing challenges in 5G transport. Danny, so I'll let you take this one kind of solo since you're the testing representative. And, we were just talking about packetizing the front haul. If that's where you're seeing particular challenges or most of them, then kind of, delve into that deeper. But generally across transport, where are the challenges for testing that you see?
I appreciate it, Sterling. Thank you. And what I'm going to be discussing over the next couple of slides, it will be identifying some of the observations that we've taken from the recent 5G transport survey, and I'll show some of the data that correlates with that. But I really like how in the previous slide, I think all three of our panelists on Kevin's slide showing not only just the way that the 5G transport has evolved, and then the breakdown of that. It was important to note that it brought us some very key points and challenges that each one of the speakers had mentioned, and I'd just like to go a little bit more into that. So as you mentioned, like the purpose of the testing challenges survey question was to determine which network performance metrics were keeping the operators up at night. What were the network architectures having challenges with, and which network performance metrics will be the most difficult to maintain once it became field deployed. And what I wanted to show in this next slide, this is one of those questions that were part of the survey. And as I just mentioned in the previous slide that Kevin showed with the evolution of that transport of 5G and the introduction of the baseband functional splits, we're really adding new levels of complexity to the xHaul transport network. And then to what Tim just mentioned and Joe prior to that is as we're adding these new transports and depending on the splits, whereas it being from the hub sites, backhaul, or even the mid-haul, each one of these packet-based transport elements are really starting to add new challenges in both the latency that was just pointed out, synchronization that was mentioned, as well as priority. So this was definitely relatable in seeing here as part of that question. A significant number of responses expressed concern regarding that network performance verification when migrating to a packet-based transport. So you could see here is both the latency measurements and the bandwidth throughput verification generated the most concern, which I think, again, this is a testament to what was that primary driven by that high-speed interfaces, as Kevin showed, up to 100 gig in some cases. And then you have the latency verification that will be essential, as I think it was Tim that just mentioned, that concerned about when you're going from CIPRI to eCIPRI and that translation there, how it's going to impact your latency, especially when it relates to ultra reliable, low latency communication applications. That you're going to expect to see more widespread in the market when the market demands it. And then we also mentioned about what is important to note, and you see here, is that we'll be discussing more of the synchronization and timing later in the presentation, but you'll know as a notable data point is the increased concern for synchronization as well as traffic priority verification when we're talking about splits. So one data point I just wanted to bring up, if you saw the survey that was taken last year, these were similar requirements that were put in that survey, but they didn't score nearly as high as far as synchronization, timing, and prioritization as compared to this year. So it really leads to the conclusion that as with the recent 5G rollouts that both the panelists that are involved with as well as myself when working directly with operators, we're seeing that demand for timing, synchronization has increased, and those challenges are becoming something much more prevalent than compared to when we were first discussing this a year ago.
Yeah, and just a note on that, we've already got a Q&A question came in that did have to do with timing and synchronization, so your point.
Yeah, we'll look forward to addressing that later on.
Go ahead.
Yeah, and then so my last slide here, but before we move on to the next section, this is just from an xHaul transport network verification perspective. The goal here ultimately is to emulate those different 5G profiles and ultimately the splits to determine what that throughput latency and that traffic shaping is met, and not just through the front haul or the F2 interface, but we're also discussing, as seen in previous slides, the F1 and the backhaul interface. So being involved in both lab and field trials, we find ourselves from a testing perspective, we're working very closely with the transport equipment manufacturers, such as the panelists that we have today, in creating these procedures and for testing and verification. And now when you add into the complexity of the introduction of white boxes, as we've also, I think we're going to discuss a little bit deeper later on in the presentation, and things such as that virtual baseband and splits, there's been an increased demand for that benchmark performance verification from operators as they virtualize that transport networks and functions. So again, this slide just briefly highlights what that bandwidth, latency, and shaping verification looks like over the xHaul, be it the F2, F1 interface, or backhaul. And we'll discuss timing and synchronization a little bit later in the presentation.
Yep.
So with that, I'll hand it back to Sterling.
Great. Yeah, and so let's, I guess, circle back, and then we are going to get right into the timing and sync, so don't go too far. But open transport networks, Tim, this is sort of where you left off on that last discussion, so I'll let you take this one. Open transport networks for 5G and the impacts of Open RAN on transport as well as just disaggregation generally.
Thanks, Sterling. So I just put a little graphic together to help us kind of think about it and talk through it. And so we definitely see increasing participation and activity growing around Open RAN. And since we've defined these functions we're calling radio units, distributed units, and centralized unit, along with the 5G core, you know, what do we want as a ecosystem community? And you know, what I think we want is, and the service providers want, is the ability for things to be interoperable, the ability to choose a best of breed path and collection of functions and elements. And so you end up with something that you want to be interoperable, something you want to be described or specified, and some alignment about, you know, how we do that. If we had 15 different specifications for the same thing, well, that wouldn't be very aligned. That would be more chaotic. And so you see the O-RAN Alliance collaborating with the Telecom Infra Project, and then you also see the GSMA and other organizations all collaborating together. And it's really around this idea of seeking to avoid any kind of a lock-in and also create a best-of-breed set of solutions. And I'll just say, you know, you really can't have Open RAN and closed transport. And so as an example, you know, we've been collaborating with the Telecom Infra Project for a number of years, And they've been working on things like the disaggregated cell site gateway and helping to define how we can go forward with an open and a collaborative and an interoperable set of solutions. And I think at the end of that, that'll pay dividends for creativity. It'll pay dividends for new entrants and new ideas and best of breed approach to how we do both the RAN and the transport. And I'll pause there.
Yeah, and I just put up the survey data point we had on this one around the white box switches and routers and their importance for overall 5G transport, and about 2/3 at least important to, in some cases, absolutely critical. I guess Joe, Fujitsu, or probably Joe, since you guys have spent a lot of time on this area as well. Any thoughts on the survey data that came back?
Sure. I thought it was interesting. Yeah, I think I'm back on. I thought it was interesting because, there is an open aspect, and that does involve or result in a fast deployment and avoiding vendor lock-in, as Tim had mentioned. So having that open environment for white box switching routers, as one example, would be conducive to having fast deployment in the overall network. And basically interoperability between the RAN and the transport, as we have found through experience, sometimes there's special characteristics that are needed on the transport to allow the RAN to communicate properly, and those adjustments have to be made. But if there was a standard that was followed all throughout, as in open, there would be a lot quicker deployment going forward.
All right. With that, looking at the clock, let's move to the next topic. On this one, and I'll bring in Daniel from Enritsu to kind of give the overview on this one. It's a big topic we could do, and we have done entire sessions on it, but sort of the bird's eye high-level view of the biggest issues in timing and synchronization as we move from 4G to 5G. And I think we do have a survey data point as well in this particular topic. Daniel, you want to take this?
Sure, appreciate it, Sterling. So yeah, just a brief summary compared to 4G. Why has the synchronization changed? And basically, what you're looking at is that when we're moving away from FDD, or frequency division duplexing, to time division duplexing, in a direct response to take advantage of having the ability to use only a single channel of frequency spectrum, TDD is becoming more widely adopted as the spectrum is being reallocated and repurposed, and to take advantage of these new capabilities. So you're talking about things such as dynamic bandwidth allocation and such. But what's critical is that TDD also requires new synchronization methods, so you can support both phase or timing and frequency synchronization, as compared to before, where FDD only required frequency synchronization. So in the next slide, we'll just discuss some of those challenges operators have expressed in the survey, as well as the testing challenges associated with it. So in this slide that we're showing now, I'm displaying the results again from the survey. And we asked basically what's the biggest challenge in each of the following sync-related items for 5G mobile transport. And one of the first observations we made, regardless of the sync-related category, you'll notice here that over 60% of the survey rated each item as a challenge, either a challenge to a significant challenge when deploying 5G mobile transport. So this is similar to my comment that I made earlier about the rising concern for packet-based timing and synchronization. As the majority of operators are deploying new synchronization methods to support that 5G, they've encountered timing challenges to meet their network requirements. So in particular, you'll notice on, again with these results, migration from FDD to TDD, the cost of out-of-band solutions, as well as replacement of non-supported PTP, or precision time protocol equipment, ranked as the greatest challenges for operators when deploying new timing and synchronization transport. With the majority of the existing 4G RANs dependent on GPS or GNSS solutions for timing, Migrating over to a packet-based sync solution could require everything from hardware replacement considerations, network restructuring, and deployment of GPS-derived or atomic clocks deployed as close to the edge as possible. So many operators have begun this deployment of packet-based synchronization through the use of PTP or Precision Time Protocol. The packet-based timing through a network has many advantages, but it's also impacted by timing errors generated from the network and system performance. So there's a 5G sync budget, and you see that on the right-hand side of this slide. And you'll notice the timing starts with the edge grandmaster clock through the transport network, and then ultimately it works from that edge grandmaster timing all the way through to the radio. And in the diagram you see, even though you have a total budget there of 1.1 microseconds of timing error through the transport, this is taken up every time that you add each network device to that route. And then you also have to take into consideration things such as link asymmetries and random error. So one of the challenges that we see, even before you get to the radio, is how can you guarantee that timing stays within its budget as it's going from that of the grandmaster or that timing reference and then working its way through the various devices. And how this is coming out, and I'll open this up to my other speakers as well, is it really is based on the class of that network element that's being added as part of that boundary clock. And you see I've defined the 3 different types, type A, B, and C, each one that adds a different amount of timing error to that total budget. So this is one of the important things from a testing perspective. We've been working with operators when they're measuring their packet-based timing error and PTP performance from their boundary clocks. They just want to ensure that they're within that budget. And that's ultimately determining the number of devices that they're able to add, as well as the type of network devices that they can add, so they can distribute that packet-based network timing without exceeding that total timing budget. So this enables operators to modify their network configurations to best suit their expected performance. So with that, I'll open it up to other comments.
Yeah, obviously it's a big topic. We've got one topic to get through and then some time for Q&A, but if anybody on the panelists on this has any comments they want to make, I'll hold, and then we'll go to the next topic.
The only comment I would add, Sterling, is there's the timing error related to core to the radio, and ultimately the handset, right, or the user device, even out here that you're showing here. But there's also the relative time error too, which is in the front hall space. If I have a kind of a centralized DU or a DU serving multiple radio units, that's even tighter, really, in terms of this radio and this radio. If we're going to do things like carrier aggregation, coordinated multipoint, or other things like that, that radio to radio synchronization and timing also is very tight. Just as a comment.
Would we say? I mean, I'm just thinking. I'm curious. For the group, would we say that the operators generally, or maybe if among tier ones, do you think they have all these problems solved largely, and it's just a matter of implementing, or would you describe their stage as still trying to figure out, what needs to be done within timing and sync for their own networks?
Well, this is Kevin here. For the large tier one operators, the timing is most critical in the front haul, and that's limited by the latency budget. So really, we're talking about spans of 10 kilometers usually or less, to keep a little bit of margin of error there. So the advantage of that is you won't have too many hops in such a short span. So Class C timing is of course required, but it's bundled in, so to speak, with the eCPRI interface. The precision timing protocol stream is kind of built in. Where it gets a little more interesting is behind the hub side. If you're taking network synchronization as a backup to GPS synchronization, then you may need the .1, .2 profiles in that part of the network.
Okay. With that, I can see we're getting close to the hour. So I'm going to extend, for anybody that wants to stay on, we'll extend about 5 minutes to take some of your questions. But we do have one last topic to hit on, which is this one in front of you. Joe, I'll let you take, I guess, kind of the solo response in this in the interest of time. But the topic, and again, this could be an hour-long discussion as well, but the need for multi-service transport supporting 5G, kind of make the case and bring in, virtualization we haven't talked about yet, but a high-level view on where virtualization would play.
Great, thank you, Sterling. Well, to address the multiple use cases with a single cost-effective infrastructure, you essentially need this commonality between all the devices, essentially trying to deploy a low latency versus high performance type of use case all on the same common infrastructure could be a challenge using traditional means. I put together a diagram or illustration shown here that goes through essentially a programmable RAN and transport infrastructure. So on the RAN side, it's using cups or distribution or disaggregation of the control and user plane, as well as on the transport side of the network. So essentially a programmable RAN and transport infrastructure for multiple networks. And beginning with the 3 parts of this illustration, there's the orchestration layer, which is blending the RAN, edge transport, and core control planes for end-to-end connectivity. And this orchestration directs the functionality of the RAN elements, the DU and the CU, essentially where the network slicing would take place, with the mid and backhaul layers of the transport. The common infrastructure consists of commercial off-the-shelf servers for the RAN elements and applications, and the edge switches offer virtualized routers for connectivity between the cell, edge, and core sites. Through this common infrastructure, multiple disparate services can be deployed using such techniques as SDN-based virtualization. And shown here, you have that first set of virtualization for enhanced mobile broadband, and then on that same infrastructure and ultra-reliable low latency connectivity all through virtualized elements that are operating end-to-end within the overall transport network. So this is essentially a very cost-effective way to do this using advanced methods in both your transport and your vRAN methodology.
All right. With that, why don't we jump right into the Q&A in the moments we have left. We have a couple questions in. Maybe I'll just kind of start on these. Question did come in from a network operator on RAN functional split expectations. What would be the different use cases for different functional splits? Can we have some examples for each of the ones that you have depicted? I think maybe, Tim, that went back to your slide way back. But if anybody wants to take that, I guess, Tim, since it was your slide that sort of prompted it, maybe give it to you.
Sure. I guess my base statement would be where you want to coordinate radio activity or the RU activity in a cluster, if you will, then you would generally want to have the DU sitting somewhere where it could reach multiple radio units. I think in general there's pretty good alignment. I'll just say this, that the option 2 split is where the CU-DU separation comes in. And generally when we talk to folks, they're thinking about the CU in a smaller collection of major kind of central offices or slash, kind of data centers. So I think there's cases where, like in the millimeter wave, you might deploy with the RU DU combined, because you've got a lot of millimeter wave spectrum and you also aren't worried about radio collaboration. And then maybe another use case is, and I think Kevin mentioned it, in your more rural area where maybe you're using low band or mid band frequencies, you could easily have it deployed as a GNB, which is an RU-DU-CU combined, just like today's kind of monolithic macro cell site. So that's your kind of at least a few examples of the deployment scenarios.
Okay.
I can give a real brief answer as well, Sterling. I think lower layer split is mandated when you've got massive MIMO antennas because there's just too much data. You need to compress it into something more efficient like eCPRI. Upper layer split is the benefit of that is when you want to virtualize some functions, take them out of the silicon and run them on a virtual machine. So you get efficiencies and pooling gain by taking this upper layer split out into a cloud architecture. So I'd say they're the two benefits of the splits.
Okay, thanks. One fairly technical, if anybody, it relates to the timing and sync, so maybe Danny, if you want to start, if able, but the question is on CRAN installations, what specific PTP precision timing protocol features are required on the switches facing the virtual DU distributed unit instances, and a question about what class accuracy is required in the DU hosting the compute nodes. Any thoughts on that? And then it mentions using the G.8275.1 profile, which is one of the two. But any comments or thoughts on that one, or if not, Danny, anybody else able to take that?
Yeah, I can briefly touch on it. There's several questions in there, but as far as some of the capabilities, I think we touched on it a little bit earlier, is that we are seeing a combination of Class B and C type recently as far as the type of class that we're seeing. And going back to the comment, I believe it was Kevin or Tim that made the comment, it really depends on, how many hops that you really have to take into consideration, and when you're looking at your total timing budget as to the type of class that you want to deploy and the number of instruments for that distribution in order to distribute that timing throughout the network. You're also seeing that depending on the class will also determine the type of clocking and holdover capabilities that the device will be capable of supporting as well in the event that holdover is required, outage or whatever it may be. In most cases that we're seeing with the deployment of edge grandmasters, as I mentioned, they're being deployed further out into the edge, so closer to that of the radios themselves, so it has less of a distance, you have less hops, you have less hardware they have to go through, that the timing budget is taken into consideration, that you have a lot of wiggle room there, that you should be falling well within it. Now, taking into consideration the farther back you move that reference, your PRTC, into the network, and the number of hops that you have to take into consideration now, that will significantly impact your timing budget and performance, and obviously that has to be taken into consideration. In most deployments, as far as what we've seen lately, .1 profile is the preferred telecom profile for PTP. So 8275.1 is the primary profile that we're seeing deployed.
All right, excellent. And we are a bit over. I pushed out for the audience. There should be a brief survey. If you can take that before you close out, we would definitely appreciate that. And maybe take one last question here. Yeah, I mean, it's a big one, but maybe a kind of a quick response on it. But we didn't get into anything around edge computing. And the question is, how is edge compute or MEC influenced by xHaul choices? I guess you could also reverse that, and how are xHaul choices influenced by MEC? But anybody want to take a final shot at that one? Some thoughts on edge compute to close out.
Well, very briefly,
why don't you go on, take it first, and then let Joe after. Yep.
Yeah, it's quick. So if you've got a hub site and you put your mobile edge cloud, adjacent to the CUDU, you can provide very low latency services because you're not tromboning the packets all the way back to a to a core that might be tens or hundreds of miles away. So having local breakout to mobile edge compute services is facilitated, shall we say, by having centralization and having this upper layer split not going very far. It's only going across the rack to the mobile edge compute cloud infrastructure.
All right.
Go ahead, Joe.
I was just going to add to that in addition to having that low latency operation in terms of your transport out to a site, typically even having that MEC at the cell site itself or at a site that's very, very close to the cell site, 10 kilometers or less. There's also a backhaul aspect. So there's the real-time operation in interacting with the MEC, but then there's updating to the MEC that would also be needed. So a backhaul channel that's also used, perhaps integrated with the front haul to provide that updating for real-time operation.
All right, and with that, we are going to have to close out here. Appreciate everybody for staying on, although it looks like people did kind of hang through. Thanks for our sponsors and speakers in particular for helping with this whole project right along. So thank you, everyone, and enjoy the rest of the day. Goodbye.
Thanks, Sterling.